Hello. Just thought I'd go ahead and submit this video for covering of chapter 10, which is worlds of gas and liquid, the giant planets. So we're really discussing basically the atmospheres and doing that planetary comparative planetology thing. So we're looking for sort of what's similar about the terrestrial planets and what's different about the gas giants, and what we'll learn is called ice giants as well. And we're using that process to try to make sense of not only how those planets look the way they do, but also why the Earth looks the way it does, and all that stuff. Plus, it's just finding out more information is always a plus. Knowledge is power. So let me start off by reading the learning goals. The learning goals for chapter 10 are one, differentiate the giant planets from one another and from the terrestrial planets. So that's that comparative planetology stuff I was talking about. Two, describe the atmosphere of each giant planet. You'll notice that Jupiter looks quite distinct. It's got a lot of stripes and stuff like that. And Saturn looks more subdued, as do Uranus and Neptune. But Uranus and Neptune have entirely different color, whereas Saturn and Jupiter look sort of the same color. Learning goal 3 is explain the extreme conditions deep inside the giant planets. You're going to see there's really huge pressures, huge temperatures, so high and so huge that you get really weird states of matter like metallic hydrogen, liquid, and super ionized water, stuff like that. Learning goal 4 is describe the magnetosphere of each planet, each giant planet. And learning goal 5 is compare the planets of our solar system with those in exoplanetary systems. So we're going to be, thinking about what we found, the many thousands of exoplanets we found so far, and how they differ from what we see in our own solar system as well as our individual planets. So let me start by sharing my screen so we can go over the PowerPoints. So I think that should be the appropriate screen. We'll find out in a second. So now I'm going to open up this one instead of the one that I did, and let's see if it still does it. Yes, it seems to be okay. And I'm going to switch to this mode. So now you can see the individual slides. I'll make this kind of small so it's not a nuisance. So I don't know why this chapter's named erroneously here, but just this first slide's bad. Everything else seems to be okay. So what causes the atmospheric features on Jupiter? I mean, look at this picture. This is a picture taken from several thousand kilometers above the surface, and man, it's just wild. All the cool stuff's going on there, all the different colors, all the different vortices. Some vortices look like they're swinging counterclockwise, some clockwise. So really, that is the big question. What are the giant planets? So how do the giant planets differ from the terrestrial planets? What are the atmospheres composed of? Where do the extreme conditions deep inside the giant planets come from? And what are the magnetospheres of each giant planet, and how do they compare to each other and to the terrestrial planets? Are there planets around other stars similar to giant planets? So it turns out, yeah, that we're going to find out that ours is not that rare, unless you want to just take what we took as our nebular hypothesis, and from that look for other systems that have formed just like that. When we take it in total like that, we don't see very many cases like ours, but we do see a lot of individual planets like Jupiter's, individual planets like terrestrial planets. Turns out the vast majority is right in between the size, meaning mass, of the Earth and the mass of Neptune. That's sort of the norm, if you will. But there's weird things like hot Jupiters that are the size of Jupiter, but less than even an astronomical unit away from their sun. Some of that's a result of us having a method of finding planets that is really geared towards finding heavy planets close to the sun, or at least initially. Now we've got other ways that are a lot more fair in terms of the statistical ensembles we get from it. So the giant planets are called gas giants, and what we mean by that is they're basically made mostly of substances that if we brought them to the Earth, they would be in a gaseous state. Jupiter, Saturn, Uranus, and Neptune, they are the giant planets. They're called the Jovian planets because one of the names of Jupiter is Jove. So they're over like Jupiter. Jupiter's about 5.2 astronomical units from the sun. Saturn's about 9.6, so it's almost double as far away as Jupiter is. It turns out also that when you get further away, We find, for instance, Uranus is about 19.2. That's almost 4 times as far away as Jupiter. And then Neptune is about 30, so that's almost 6 times as far away as is Jupiter. So they really are spaced far apart. And here's an oddity: if you exclude the rings, basically, you can actually fit all the planets between the Earth and the Moon. So their diameters, though big, are still not that big compared to the orbit of our Moon. So this is them on a scale where they're all basically on the same scale, so you can see how their relative diameters compare. Jupiter turns out to be about basically its radius is about 11, a little bit more than 11 times bigger than Earth. So you'd have to stack up a little bit more than 11 Earths on top of each other to make the diameter of Jupiter. Saturn's a little smaller than that, but not hugely smaller. It's about 9.4 times the diameter of Earth. And then we get a little smaller when we start talking about Uranus. It's 4 Earths tall, and then Neptune is just under 4 Earths at 3.8. So that gives you some ideas of relative sizes. There's the actual table where you can see that data from. So you see Uranus and Neptune are smaller and have much more water, ice, and other ices. Remember, Jupiter and Saturn were the ones that really got so big that they could hold on most of the hydrogen and helium that they picked up. And because Uranus and Neptune are so much smaller, they couldn't hold on to that hydrogen and helium so well. So they have a lot more of the other stuff. It turns out, we're going to see a lot of the colors that you see are a result of methane and ammonia and stuff like that. So they have methane gas, ice, and ammonia ice, and water ice. They call those outer 2 planets, Uranus and Neptune, the ice giants, because obviously they have a lot more ice. Something else that's kind of interesting is notice the actual tilt. Something odd about the tilt of Jupiter is only about 3.13, so you wouldn't expect it to have extreme seasons. Saturn actually has 26.7 and Neptune has 28.3, so they're sort of like we expect on Earth with our 23.5 degree tilt. But the crazy thing is Uranus is actually tilted. They usually call it a negative 97.8 degrees because it's literally just lays over on its side and sort of spinning backwards. So that actually leads to basically half of a Uranus year, which, as you can tell from this table, is half of it would be about 42 years, is spent with the north pole or the northern hemisphere of Uranus being in sunlight, and the other half is spent with it being in complete darkness, or nearly complete darkness. So that's some crazy things that happens with these planets. They're called gas giants because their mass, are called giant planets because of their mass. 14.5 Earth masses for Uranus, 318 for Jupiter. So Jupiter is literally 318 times the mass of the Earth. To give you some comparison of that, well, I'll just leave it at that. It's 14.5 Earth masses is what Uranus is, and then 318 is what Jupiter is. Jupiter is actually sort of compacted more than it normally would be. Notice it's not much bigger than Saturn. That's because the layers of gas on top have compressed the layers below it so much that even though it's remarkably higher in mass, the radius isn't that much bigger. It's just it can't, basically the gravitational force isn't strong enough to push it but for so hard, but at the same time the pressures of the gases inside are actually keeping it at bay. So it's a neat little equilibrium that's established within Jupiter. They essentially have no solid surfaces. If you just flew into it, you'd see cloud layers, but the clouds would get denser and denser and denser and just make a sort of smooth transition into a point where you just couldn't traverse any further because it's just too hard. So it's sort of like slowly running into a solid surface, but really there's no clear demarcation where that is. We actually measure the size of them by basically looking at starlight and seeing how long it takes to be eclipsed by the intervening planet. Stellar occultation is what it's called. And we know the relative velocity of the Earth to the planet, and then basically the amount of time that we go without seeing the star gives us the size of them. And by size, again, in this case, we're meaning the actual diameter. The masses can be found by observing their moons orbiting them. That's a very accurate way. We just use Newton's law of gravity. with the way Newton actually did it as opposed to the way Kepler did it, because when Newton did it, he actually derived it and gave us a result for the actual constant that relates the cube of the semi-major axis to the square of the period, and that constant's related to the total mass of the system. So we can actually determine the mass of the major planet by comparing the cube of the semi-major axis divided by the square of the period. Excuse me. So we can use that to find the planetary masses, and of course then we have the size, so then we can come up with the density pretty well. And we see that basically these gas giants run from a little bit less than the density of water up to around 1.6 times the density of water. Saturn's actually less dense than water, and if you could find a big enough ocean that would sit still, you could dip Saturn in it and it would float. So the outer two, Uranus and Neptune, are markedly more dense in some ways, but none of them are as dense as our terrestrial planets. Jupiter and Saturn were known to the ancients. Uranus and Neptune were actually found by telescopes, so they didn't really know about those, even though you could have actually seen Uranus even through Galileo's scope. I think there's even some data suggesting that Galileo just didn't know what he was looking at, and he actually spotted Uranus through his telescope at one point, but just didn't study it long enough to realize it was another planet. Uranus was discovered by Herschel by accident in 1781. He first thought it was a comet, and then of course you follow the orbit and you see that can't be it. And then of course later Uranus was discovered to have some oddities in its orbit, so from that they were able to predict mathematically that there'd be another planet, and lo and behold, Gale, G-A-L-L-E, I'm not sure how to pronounce his name, went out and looked for it where it was predicted by Leverrier and Adams, and lo and behold, there it was. In 1846, they found it. The gravity of Neptune was actually tugging on Uranus, and that's what made it orbit a little different. More giant characteristics. Well, we see atmospheres, not surfaces. Again, there's really no strict line between the surface and the atmosphere, but the densities, like I said, range from 0.7 to 1.6 times as dense as water. Earth's density, like I said, is around 5.5 grams per cubic centimeter, or grams per milliliter, and the density of water is 1, so that's why it goes 0.7 to 1.6. Jupiter's chemistry is mostly hydrogen and helium. Saturn has a little bit more heavy elements, but it's mostly like Jupiter. So Saturn, or let's say Jupiter, is essentially the same composition as our sun. Saturn is almost the same, but it has a little bit of heavier elements. But remember, in astrophysics, heavy elements mean lithium and above, so anything heavier than hydrogen is considered a heavy element. Uranus and Neptune have many more heavy materials, but mostly methane. All giants have rapid rotation and therefore different amounts of oblateness. This picture right here is actually showing the fact that Saturn is quite squished at the poles and quite wide at the equator. As you can see, there's much more light at the north and south pole. The white light is quite a bit thicker than the white light at the equatorial ring, or the equatorial area. They also have different obliquities. Jupiter's tilted at 3, Uranus at 98, and of course the 98 results in extreme seasons. Jupiter has strong dark bands called belts, and then light bands called zones. So these are the bands, and these are the zones. There's a long-lasting giant storm. It's been there ever since Galileo first looked at it. We know it's been there obviously before then, but that was the first time we confirmed it was there. So it's called the Great Red Spot, and it's roughly almost 2 diameters across it. 2 Earth diameters across it. In fact, this lab this week you're doing is actually going to have you try to estimate how big that is, and then use that to calculate how fast it turns. Little hint: if you take the biggest axis across it, in other words, the longest line across the oval, and pretend that's the diameter of a circle, you'll get a circumference that's a little bit bigger than the ellipse. And then when you take the smaller axis of the ellipse or the oval and assume that's a circle, you'll get a circumference that's a little bit smaller than the circumference of the oval. So if you take the average of those two, you can get a pretty good estimate of the circumference. Just remember that pi times the diameter is the actual circumference. So you can look up the circumference of the Earth, or excuse me, you can look up the diameter of the Earth, and then use that to compare to the sizes that you see in that lab. So hopefully that'll give you a little bit of a head start on that, working on that lab. There are also many smaller storms, and the colors indicate basically a really complex chemistry. So, uh, some colors represent hydrogen sulfide, uh, others represent other chemicals, nitrous, or excuse me, ammonia, methane, stuff like that. So you'll see in all the other planets. But here's a picture, for instance, near one of the poles, and you literally see 8 different vortices. So it is quite complex. We don't understand all the details about Jupiter to this day. We don't know what's causing that storm. Why is it that particular spot? Is it actually stuck to that particular spot? Can you actually use that spot to determine the rotation rate of Jupiter? It seems that you actually can't. In fact, there's other ways we use the magnetosphere to help us find those rates. But pretty interesting stuff that we just don't know about still about the stars. I mean, about the large planets. The cloud patterns show basically like a jet stream forming. Saturn has a similar band structure to Jupiter. The big problem with Saturn though is it's less pronounced. You can see the bands and the zones and stuff through here, but notice how they don't show up as much. And that's basically because this outer atmosphere is a different chemical, and that chemical isn't cold enough yet to actually condense out into clouds. So you basically got like a haze over top of the cloud formation. So we're not seeing it. In this case, we're actually seeing a storm that existed on it for some period of time, if I remember correctly. It does have violent storms, similar to Earth's jet stream. It has a jet stream, and they wiggle back and forth between low pressures and high pressures. Remember, low pressure zones are like hurricanes, and we call them a cyclone. And then high pressure zones are like the opposite of a hurricane, and we call those anticyclones. It turns out that red spot on Jupiter is, in fact, an anticyclone. Big one, though, like I said, twice the diameter of the Earth. The cloud patterns on Uranus and Neptune, those are also sort of subdued as well, because you've got, again, another layer of atmosphere with very little cloud formation. And then you go deep through that hazy atmosphere before you actually run into cloud formation. So we don't get to see quite as much. Infrared observations show details of structure on Uranus. There's weak banding of both Uranus and Neptune. There are small scattered bright or dark clouds, and those planets have transient large storms. So storms appear and disappear and stuff like that. Again, they're just a little harder to see. Of course, all the outer planets, remember, they also have rings, but they're a lot more wispy than the ones that Saturn has. So under the cloud tops, if you look at this, these are plots of pressure and altitude versus temperature. If you look on the left, that's Jupiter. On the right, that's Saturn. And you'll see basically if you go to an altitude, basically they're calling it 0, where you can see a little haze, and then there's a stratosphere above it where it's essentially clear, and that goes up to 100 kilometers above that. And you go down to about 150 below it, and basically it's broken down into the innermost part, basically has gaseous hydrogen, helium, methane, ammonia, and water. And then the water and ammonia droplets actually precipitate out in this area right around in here. So you end up getting water ice and ammonia ice clouds, and then ammonium hydrosulfide ice, and then ammonium hydrosulfide type clouds, ammonia ice. The troposphere occurs, and then you have the haze. Notice how the temperature runs, though. It starts at like 400 Kelvin, which is plenty hot. And then it dips, gets colder and colder and colder, reaching around 120 Kelvin roughly at the haze layer, and then it starts to increase again as you're getting, sort of not really closer to the sun, so to speak, but closer to the outside of the atmosphere where the sun can directly interact with it. If you look at the pressure side, you see that in fact we're going to reach on the order of this is 2, that's 10, so this is probably 20, 40 atmospheres, somewhere around there. So you get some really high pressures under the surface of Jupiter. Saturn, sort of the same thing that you see with Jupiter, but not quite as severe a range of temperatures. You do have that water and ammonia droplets, but they're occurring way down deeper. In fact, negative 300 instead of negative 150. And then water ice is appearing, and ammonium hydrosulfide ice is appearing, and then ammonia ice, and then the haze. And what you see is you got this 200-kilometer area that's all sort of dimming that pretty stuff, whereas this one's only got about 75 kilometers dimming it. So that's why Jupiter looks much more brilliant. The gas giants have similar cloud layers. Their temperature and pressure increases downward. The clouds layers have different heights, and clouds on Jupiter consist of ammonia, ammonium hydrosulfide. Ammonia is NH3, of course, and that actually precipitates out at 133 Kelvin, or excuse me, freezes. And then ammonium hydrosulfide, NH4SH, does so at 193 Kelvin. If you look at Uranus, it sort of has the same stuff, but a lot less of the hydrogen. So you start down at a negative 150 kilometers, you're running into water, ammonia, hydrogen sulfide droplets, and then water ice, ammonium hydrosulfide ice, hydrogen sulfide ice, methane ice, which gives it that characteristic greenish color. And then you subdue that a little bit more with Neptune, push it a little lower, and you lose some of the green and get more of the blue. That's why Neptune tends to be a little more blue. So you can see on the right that Neptune has its methane layer a little lower than Uranus does. So, and obviously impurities can make the different colors as well. So if you don't have exactly methane, it's not going to be exactly the same blue every time you look at it. Similarly with the different bands and colors that you see on Jupiter. The highest clouds of Uranus and Neptune are methane ice. They are bluish because of the scattering by methane, and the clouds on Jupiter and Saturn are colored by the impurities. If you look at the actual wind speeds for Jupiter, you see that it has really huge wind speeds of 550 kilometers per hour, for instance, around the equator, and then they diminish. Of course, they wiggle back and forth. Some are going to the east and some are going to the west in different regions, not unlike, you know, our doldrums and all that stuff that we have on the surface of the Earth. And what's driving that is the internal heat and heat from the sun, basically causing the global circulation patterns. The Coriolis force, of course, plays a big role here. So because it's such a large mass, the rapid planetary rotation results in a strong Coriolis force. Remember, these planets orbit, or excuse me, rotate way faster than the terrestrial planets do. If you look at Saturn, it has even faster winds, 1,650 kilometers per hour. So you're looking at, you know, 300 miles per hour common winds at the equator of Jupiter. And if you want to look at, say, Saturn, we're looking probably 1,000, 1,200 or something miles per hour for the velocity there. So the most extreme equatorial winds are in Saturn and Neptune's atmospheres with maximum speeds up to 2,000 kilometers per hour. It's pretty daunting. If you look at Uranus's winds and Neptune's winds, you see sort of a slightly less complicated pattern. Basically, they're all one way along the equator, and then they deviate the other way as you get closer to the poles. And less is going on actually with Neptune. So alternating east and west winds make banded clouds on Jupiter, and the circulation pattern differs from planet to planet in ways we just don't understand. So planetary astronomy, even though it's not my favorite subject, but it is a lot of really interesting stuff going on that's yet to be understood and explained. If you look at models of the interior, it turns out we have a rocky core. That's our best hypothesis right now, and I'd say it's pretty close to becoming a theory, but we have rocky cores in all of them. And then they're surrounded by liquids and ices, and then metallic hydrogen and metallic molecular hydrogen. These are crazy things. You don't see hydrogen in molecular form, and you certainly don't see metallic hydrogen anywhere, but molecular hydrogen, you only see that around Earth. You don't see that in outer space usually. So on Jupiter and Saturn at depths a few thousand kilometers, the gases are compressed so much that they actually liquefy, and you actually get metallic hydrogen. So metallic hydrogen means, one, it's metallic, so it's a conductor. That means basically it's under so much pressure that it has such a high temperature, its atoms has such a high speed that they run into each other so frequently that the electrons have busted loose, and it actually acts as a conductive material. For instance, liquid hydrogen acts like a metal there, and it's because of Jupiter's core pressure of 45 million bars. Okay, remember a bar is about the same as 1 atmosphere, so we're saying 45 million times the pressure of the surface of the Earth. Jupiter's core temperature is about 35,000 Kelvin. That's way hotter than the surface of the sun. The cores are a liquid mixture of water, rock, and metals, and there's no clear-cut boundary between the atmosphere and the underlying oceans. But they do have those ionized liquids that are rotating, and of course you'd expect magnetic fields to come from that situation. Uranus and Neptune are smaller and have less pressure than the gas giants. They have way more water and ices, specifically ammonia and methane. Deep oceans containing dissolved gases and salts are present, and computer simulations suggest that the water on the ice giants is probably super ionic, a state between liquid and gas. So they're basically a lot looser packed than water would be. And they're ionic because they actually have broken up, into the individual ions that make up the molecules and atoms of the water. The magnetic fields all sort of act like bar magnets, just like they do on Earth, but notice the weird shifting of them. So for instance, Jupiter has a north-south bar magnet that is not really lined up very well to the rotation axis. I think it's off by like 13 degrees or something like that, but the center lines up pretty close to the center. Saturn has one right on the money. I think it's a couple degrees off the tilt from the from the rotation axis of Saturn, and the center is really spot on. And then you get to Uranus, and it's like, what the poop? It looks like basically the center of Saturn is almost a third of the way away from the center of, the center of the magnet is almost a third of the radius of Uranus away from the center of Uranus, and bears essentially almost no, resemblance to the rotation axis. It's like a good 45 degrees. And the same thing with Neptune, and its center shifted even more, maybe 2/3 of the radius down. Again, we don't really understand this. We don't understand as well as we'd like how magnetic fields are formed anyways, but it's really crazy when you look at these type of magnetic fields and weird bar magnets that have to result. The magnetospheres, basically that area where the solar wind starts to interact with the magnetism of the planet. And other than, of course, the magnetosphere, say, of the sun, Jupiter's magnetosphere is the biggest thing in our solar system. And not only that, because Uranus, for instance, Uranus and Neptune have their bar magnet off center, so each time it rotates, you're actually having not only just a magnetosphere that's rotating, you have a magnetosphere that's shifting and basically forming like a helix shape or a spring shape, if you will. So that's kind of neat. That creates what we call synchrotron radiation. And we can actually look for the peaks and troughs in that and use it to better determine the actual rotational periods of those planets. So the magnetospheres are huge. For instance, in Jupiter's case, it's 6 astronomical units long. And remember, it's only 5.2 astronomical units away from the sun, whereas Saturn's just over 9. So you can see that clearly the magnetosphere of Jupiter is smoking Saturn all the time. The magnetospheres do interact with the solar wind. They cause the auroras. Remember, the way magnetism works is basically when you have a velocity of a charged particle, it's going to create a force that's perpendicular both to the magnetic field line as well as perpendicular to the velocity of the charged particle. And that ends up making them spiral around the actual field lines. So that means they're going to follow field lines as opposed to being shifted away from them or something like that into their point of highest density, which is normally the north or south poles. Obviously, it's a lot different with Uranus and Neptune, as we saw how crazy their fields are. So the magnetospheres do produce auroras. We see them. We have evidence of them. We can see crazy stuff like stuff inside the clouds being ionized and having crazy lightning from one cloud to the other and cool stuff like that. So really some cool pictures. Definitely recommend you check them out. You'll see some in your book, but there's even more on the internet. The effects of the magnetic fields are basically strong magnetospheres can concentrate charged particles in the radiation belts. And for instance, there's an Io's plasma torus. So basically, Io's putting out basically all sorts of gas, dust, and particles from its numerous volcanoes, and then the magnetic field lines are interacting with that, and it causes this torus, which is a mathematical term for the shape of a donut, like Homer would love. Donut. But anyways, one radiation belt is the plasma torus. It's created by particles from Jupiter's moon Io, and it creates what we call powerful flux tubes. So they create really cool auroras. You can see them in these little blue lights here and here and here and here, and they spiral around the pole. It's really would be an amazing sight if it wasn't for the fact that you're going to die if you even enter that atmosphere. Turns out our solar system's not that typical. It's not very normal based on the thousands of systems we've seen to have a bunch of rocky planets on the inner part and a bunch of gas giants on the outer part. It turns out we have sort of mixtures. We have, like I said, hot Jupiters, super Jupiters, puffy Jupiters, super Earths, mini Neptunes, all sorts of crazy stuff. In fact, if you look at Kepler 20a, a G star, you actually see a big planet followed by a small planet, followed by a bigger planet, followed by a bigger small planet, and then somewhere in between. So really crazy stuff. The hot Jupiters basically orbit up to half an AU away from their star. So they're, basically something the size of Jupiter, but twice as close to the sun as the Earth is. Puffy Jupiters have a larger radius and lower density than Jupiter. That means that basically the stuff is there. It's a huge amount of matter, but it's not packed as tight as Jupiter is. Super Jupiters have masses that are 2 to 13 times Jupiter's mass, so that's really big. And then super Earths and mini Neptunes seem to be the more normal scenario. In other words, the majority of systems we run into have a lot of things that are slightly bigger than Earth or slightly smaller than Neptunes, 1.5 to 10 times the Earth radius, for instance, or mass, for instance. So that pretty much covers the chapter 10 material. I hope I explained it pretty well for you. There's not any real big topics that jump out here. Remember, once we've got through the science part in chapters 1 through 6, this is more like a typical first biology class where you're learning some basic facts, applying the science that you learned earlier on to make sense of the science that you're learning so that you can build narratives as opposed to just memorizing disparate facts. Process of science is a good way of thinking about that. So for instance, Neptune was predicted before it was found because Uranus's orbit was not matching predictions made by Newton's laws. That's a case where we actually had some evidence to predict something we'd never seen before. This happens quite a bit in physics or in science in general. I told you before that Dirac had worked out a really nice equation for quantum mechanics that was consistent with relativity, and the energies that came out of it were negative, and that just didn't make any sense to the physics world. But Dirac was pretty confident his equation was right, so he said there exist particles that will behave oppositely to the particles we know. So there will be like anti-electrons who will have a positive charge and anti-protons that will have a negative charge. And lo and behold, he was right. So that's kind of crazy. But reading through the process of science essays are good. And remember, you always can get extra points by completing any of the things at the ends of the chapter. I hope that helps you. Y'all have a good time. Stay safe. Make sure you make notes of anything you didn't understand, either from the reading or from my discussion. And I'm going to post this. It should be up in the next 2 hours. It takes that long to render. Have a good day. Bye-bye.